OMG, we're back with another video. We're doing some particle motion. Let's jump into it. Boom. All right. This is question 2 from the 2021 free response questions. Question 2 says, a particle P is moving along the x-axis. The velocity of particle P at time t is given by vpt equals sine of blah between 0 and pi. At time t equals 0, particle P is at position x equals 5. So they gave us a velocity function and an initial position, an initial condition, if you will. A second particle Q moves along the x-axis. The velocity of particle Q at time t is given by that velocity function between 0 and pi. And again, an initial condition of at time t equals 0, particle Q is at position 10. Find the positions of particles P and Q at time t equals 1. So again, it doesn't matter what type of question you're looking at. It doesn't matter if it's people getting on an escalator. We had that question. It doesn't matter if we're talking about some random graph. It doesn't matter if we're talking about a particle. The integral of a rate gives you position. So in this case, gives you a value, I should say, right? But often it's a position, and the integral of velocity will give you the position. So we want to integrate these, okay? So why is my pencil not wanting to connect? So we're going to integrate. So the position function is going to be the integral of that velocity function. So if we're, let's do position as s of p. Oftentimes s is position, sometimes x is used as position, but I'm going to use an s. So s subscript p of 1, right? Because they're asking for what is the position after 1 second. So if we're finding the position after 1 second, we're going to use the initial condition of particle P, which is the position at t equals 0 is 5. So we're going to take that condition and say 5 plus the integral from 0 to 1 of the velocity function. And that is going to give us our solution, okay? That's going to give us our position. So, because this, what is this solving for? This is solving for how far the particle moved, and this is telling us where the particle is already. So the initial condition plus how far the particle moved will give us our new position. This is a calculator question, so I'll put that into the calculator in a second. And similarly, for particle Q, we want the same thing. Its condition was that it's at 10 on the x-axis, and we're doing the same math except with the other velocity function, okay? So there's our two functions, our two values that we need to find. So let's pull up the calculator. And I'm not going to dual screen it up here. I'm just going to put it on my other monitor. I'm going to type in the velocity function. I'm going to go ahead and save the velocity function for particle P as P of t, because I don't want to use V twice, of course. So I'm going to do P for particle P. So I'm going to type in trig sine of t raised to the 1.5, and I'm going to save this. I'm going to store this, I should say, as P of t, just so I can use it later, right? That's something that I like to do. And then I'm going to do the same thing for the other function. I'm going to say t minus 1.8 close parenthesis times 1.25 raised to the t. That's the q function, the velocity of q. So I'm going to store that as q of t. Okay? Q of t. So the math that I had previously written down is, if we close this up. If we, that's not what I want this. If we take that initial condition and add it to the integral, we're going to get our new position. So that's going to be 5 plus, I'm going to hit, can I make this maybe a little bit bigger for you? Does that help? I don't know. So I'm going to do 5 plus 4 for calculus, and then 3 integral, and I'm doing this from 0 to 1. Why is it from 0 to 1? Because they're wanting to know the position at t equals 1. If we wanted to know the position at after 2 seconds, we'd go from 0 to 2, okay? And also, mind you, it is starting at 0 because they told us the position at time 0, right? Like the particle p is at position 5 at t equals 0. But what if they told us the particle p is at position 7 at t equals 1? Oh, well, then your integral would start at 1 and go from 1 to, say, 3 if the question asked for the position at t equals 3. So the bottom bound is the initial condition, like when the initial condition was happening, and the top bound is where you're trying to get to. So they gave, hopefully, I'm not trying to super over explain, but I'm just saying like a generality here, trying to give you some tips here. So if I plug that in, I get a lovely 5.371. If I round that to the thousands place. Okay, cool. And then I'm going to do the exact same thing. Honestly, just to show you a reminder, right? Control C, Control V. Just go ahead and paste that in there. Change this P to a Q now because we're talking about particle Q. And then change this 5 to a 10 because the initial condition was 10. And boom, just like that, I've got 8.564. So there are the two positions of the particles. Shall we continue? We shall. So are particles P and Q moving toward each other or away from each other at time t equals 1? Explain your reasoning. Okay, so let's maybe draw a picture to help ourselves. At t equals 1, it asks. So here's the x-axis. Here's 0. Here's 10. And here's about 5.371. This is particle P. And here's, 8.564. This is particle Q. What we're wondering is, are these particles moving away from each other? Or are they coming towards each other? Or what's the situation, right? They could both be moving left. They could both be moving right. They could be coming at each other. They could be going away from each other. There are basically 4 different options. And the question is wondering, again, are particles P and Q moving toward each other or away from each other? Explain your reasoning. So it comes down to the velocity. If the velocity is positive, the particle is moving to the right. If the velocity is negative, the particle is moving to the left. Okay? Positive velocity right, negative velocity left. So we simply need to evaluate the velocity of both of them at t equals 1. Luckily, we have both of them saved in our calculator. So P of 1, in other words, I'm calculating the velocity of particle P at t equals 1, and I got 0.841. I'll jot that down in a second. And again, I already have the velocity of particle Q saved as Q of t. So Q of 1 is going to come out to be, you can't see it. Here, let me just type a random number so you can see it. Boom. Q of 1 is -1. So particle P has a positive velocity and is therefore moving to the right. Particle Q has a negative velocity and is therefore moving to the left. So it does say to explain your reasoning. So we need to be precise here because explain your reasoning is important and requires specific detail. So we're going to tell our grader that the velocity of P at 1 is 0.841, which is positive, and the velocity of q at t equals 1 is -1, which is negative. It's also important to note that P is to the left of Q, right? So particle P is actually moving to the right. That's what it's doing. And particle Q is actually moving to the left. That's what it's doing. So they're coming at each other. But they wouldn't be coming at each other if particle P was over here, right? If particle P was over here and moving to the right, and particle Q was over here and still moving to the left, they'd be moving away from each other. So we need to tell our grader two things. We need to tell them the direction of the particles, but also where they're at. So we can say particle P and Q, whoops, started to write Q in the word and Q are moving towards one another because V of P is, or V of P of 1 is greater than 0. V of Q of 1 is less than 0. And P. Okay, let me look at my official wording. At time t equals 1. Oh, yeah. At time t equals 1, particle P and Q are moving towards one another because V of P is greater than 0. Thus, moving right. And V of Q is less than 0, thus moving left. And 5.371 is less than 8.564. Boom. Okay, that was clunky, right? Sorry, that was clunky, but I'm trying to be precise, right? What am I trying to tell my grader? I need to tell my grader that P's over here, right? Or, well, here, let me not use my hands and let me just circle. P's over here on the left, Q's over here on the right. So because P's on the left and moving right, and because Q's on the right and moving left, they're coming towards each other. That's what I'm saying. Okay? So this is to the left of this. This is moving right. This is moving left. So, yep, they're coming together. All right. If I look at the key for that, just to show you, well, I forgot to show you the key for the first one. The definite integral gets you a point. One of the positions gives you a second point, and the other position gives you a third point. So you could mess up one and still get 2 out of 3. You don't have to get them both simultaneously. So that's interesting to note. The direction of motion for one particle. So if you tell them that one of the, like if you, so yeah, if you clarify that this particle is moving to the right, you're going to get a point. So mentioning direction gets you 1 point, and then tying it or putting a bow on it with an explanation gives you the other point. And look at what they're listing here. So they told us one particle is moving to the right, one particle is moving to the left. They told us the positions, and thus at time t equals 1, particles P and Q are moving toward each other. You know, I am noticing their notation here. I said the numbers. I think I would need to say, and thus P is to the left of Q. I think I would need to say that. I think you would need to say that. let's move on. I'll try to be more precise in the next one. Find the acceleration of particle Q at time, oh, I won't give away the answer yet. Find the acceleration of particle Q at time t equals 1. Is the speed of particle Q increasing or decreasing at time t equals 1? Explain your reasoning. So again, that means we need to have a full-on sentence here, okay? Acceleration is the derivative of velocity. So we want to derive the velocity of Q and evaluate it at time t equals 1. You follow? We derive velocity to get acceleration, and then we want to plug in the number 1 to get the actual acceleration. So let's bring up the calculator, and we're going to derive the Q function and plug in the number 1. Now, I don't think we're going to use acceleration again. Let's see. Yeah, we're not going to use acceleration again in the next question. So let's use the lovely menu for calculus, derivative at a point. Actually, I don't remember how to use this function, so I'm not going to do it. Sorry. I forget how to use that function. So we're going to do I'm just going to do derivative. Okay, so let's derive with respect to t. What are we deriving? The Q function, because we want to know the velocity of Q. And I made Q, the Q function, the velocity of Q. So bada bing, bada boom. There is the acceleration function. I'm going to click up, and I'm going to Control C. I'm going to copy it. I'm going to Control V. I'm going to paste it. And then I'm going to replace that t with a 1. I'm going to replace this t way over here with a 1. Hit enter, and I got 1.02686. So I'm going to jot that down. So the derivative of the velocity function is the acceleration function, and the acceleration at t equals 1 is 1.027. Oops. Okay, this is what I wrote down. I'm telling my grader that I know that the acceleration function is the derivative of velocity, and then I'm plugging in the number 1 into the acceleration function and getting 1.027. Okay? Now, let's continue reading here. It says, find the acceleration. So this would be, in proper units, would be, well, they haven't really been specifying units, have they? So I don't think it matters. And then, is the speed of the particle increasing or decreasing? So speed comes down to whether velocity and acceleration complement each other, meaning they're the same, or whether they're working against each other, meaning that they're different signs. Okay? So if velocity and acceleration are both positive or negative, it's speeding up. If velocity and acceleration are opposite signs, it's slowing down. So we already calculated the velocity of Q. It was -1 at t equals 1. So if the velocity is negative, but the acceleration is positive, we are slowing down. Is the speed of particle Q increasing or decreasing? It is decreasing. So here, let me be precise with my words and give you a really good example here. Take their words and spit it back out at them. Is the speed of particle Q increasing or decreasing? Take out the word is. The speed of particle Q is decreasing at time t equals 1 because AQ of 1 and VQ of 1 have opposite signs. Boom. That's what you need to say. Take their words and spit it back at them. And then the why, explaining your reasoning, is because they have opposite signs. If I go to the scoring guidelines, let's see how well I did. The speed of particle Q is decreasing at time t equals 1 because the velocity and acceleration have opposite signs. Look at that. Now, they did write this statement: velocity is less than 0, acceleration is greater than 0. I don't know if that is 100% necessary. The response does not need to present a value for velocity, so you don't need to remind them about velocity. Earn the second point, a response must compare the signs. Oh, right here. After the first response has been earned, a response declaring only velocity and acceleration are of opposite signs at t equals 1 earns the second point. So you don't have to be super extra about it and like say everything again, right? I think that's the lesson to be learned here. You don't have to like keep repeating yourself. All right, and find total distance traveled by particle p over the interval 0 to pi. So total distance traveled is different than where is the particle, right? Because if I'm a particle moving on the x-axis and I'm moving left and right, if I'm a particle moving on the x-axis, moving left and right, I can move left, right, left, right, left, right, and then end up right back where I started. My total distance traveled, I traveled a lot of distance, but my position is the same. So total distance and position are not quite the same. So how do we do that? I mean, if the integral of velocity gives you position, can we integrate velocity to give us total distance traveled? Because it's kind of the same thing. And the answer is yes. Why does an integral give you position? Because an integral accounts for positive velocity and negative velocity, moving right and left. It accounts for those things and cancels out, right? But if you take the absolute value of the velocity function, you're making everything positive. So those movements left and movements right are no longer canceling out. Instead, it's just adding all together. So total distance, we have said in the past, is that the total distance equals the integral, and it asked for 0 to pi. That's why I'm using 0 to pi, of the absolute value of the velocity function. And which particle are we talking about? I forgot. Particle p. Okay, that is our expression. This is what we want, the absolute value, and that will give us total distance. Again, this is something that's simple enough to plug into the calculator. That's menu, 4 for calculus, 3 for integral, 0 to pi. Pi is right here. Boom. Of the velocity's particle function, but the absolute value, right? So absolute value is hidden over here beside the number 9. You click this. There's all kinds of options, and we want the absolute value. And the velocity function of the particle p is still p of t in our calculator. It still remembers that. With respect to t, and we get 1.931. 1.931. Everything needs to be rounded to the thousands place as a nice gentle reminder, and we're done. There it is. Hope you enjoyed that. I hope you learn from me just taking the words and spitting it back at them. I encourage you to read through those scoring guidelines and understand the nuances, right? I want it to give you relief that there are exceptions to be made, but at the end of the day, they are looking for something precise, and I hope you're starting to understand that preciseness. My lovely 4 pages all typed up of common justifications and explanations is where you want to go. This is one of those explanations. Opposite signs, slowing down. All right. Thank you for watching. Enjoy the rest of your day, evening, morning, whenever, and wherever you are. I'll catch you in the next one. Ta-ta for now.